Hello everyone, my name is Yohei Sato from Portia Institute, and the first author is Lubomir Press from also Portia Institute and EPFL. Today, we want to talk about the computational study of force balance during nucleate boiling. Nucleate boiling is one of the most efficient modes of heat transfer, and the evaporation heat flux is proportional to the bubble departure volume multiplied bubble departure frequency. So, to predict evaporation heat flux, it is important to predict bubble departure volume or bubble departure diameter. And many modelings have been proposed. For example, Fritz model, Zuba model. And in this study, we focus on saturated nucleate pool boiling. The conventionally detachment assumed to be occur when Fz, the force acting on the bubble in z direction, is larger than 0, like this equation. And here, P is the momentum of bubble in z direction. But last year, Butch published one paper which experimentally shows that this Fz equals almost 0 throughout the entire bubble growth cycle. This means that the conventional approach, Fz is larger than 0, this approach is inadequate to predict bubble departure diameter. And new modeling is required. The one possibility is using CFD method, simulation. And this work is the first step in model development. For CFD simulation, we use in-house PSI boil, CFD code, PSI boil. It uses geometric VOF with sharp interface phase change modeling and conjugate heat transfer between solid and fluid are taken into account. The simulations of a single bubble growth under different intensity of gravitational acceleration were carried out. The gravity acceleration was 0 or plus minus 9.8, that is 1g, and 10g. We used two approaches. The first approach is pure DNS, in which we fully resolve micro layer. But because of small grid, we can simulate small domain, and we can simulate only short period. In approach 2, the partial DNS was performed. That means velocity and pressure are directly computed, but the phase change rate and the micro layer is modeled as a subgrid model. In this approach, contact angle hysteresis is also taken into account. And as a result, we could simulate full bubble growth cycle. The coordinate system was axisymmetric coordinate system, and the heat flux is about 400 kilowatt per square meter. It's the same condition as the Butch's experiment. So I talk about micro layer, but I need to explain what it is. So micro layer is a thin liquid film layer underneath a growing bubble. And because of this thickness, thickness is the order of microns, and the temperature difference is quite big between the liquid paper interface, which is the saturation temperature, and the wall. As a result, we expect the higher heat flux in the micro layer, which reaches more than 1 megawatt per square meter. Here's a computational domain. The computational domain consists of fluid domain and solid domain. For pure DNS, the grid size is 1 micron, and the computational box size is 1 millimeter. But for the partial DNS, it's 10 times bigger than the pure DNS. The modeling of forces. We follow the Butch's modeling of force modeling. In this approach, the total force is assumed to be FP, buoyancy force, plus adhesion force, FA, plus FP, that's the pressure difference force. The pressure difference force takes into account the hydrostatic pressure and also the pressure due to curvature or surface tension. And in the experiment, they calculated these forces based on the photo, and the result is F total is almost 0 during the bubble growth period cycle. Here I want to show one example of temperature distribution based on pure DNS. Here you can see the hot spot, and the vapor phase temperature is higher than the saturation temperature. And here it's difficult to see, but there is a micro layer directly captured with the simulation. And the receiving contact angle here is set to 1 degree. This is the temperature distribution of partial DNS. In this case, we can simulate the entire bubble until the bubble temperature. And advancing contact angle is given as 55 degrees. Bubble profiles. The left figure shows the bubble profiles at 1 millisecond using pure DNS, and right figure is partial DNS. And in each picture, you can see three lines which represent the blue one is hyper G, this is 10G case, and orange is 0G, and inverted G is -1G. So as you can see here, these three lines doesn't differ so much. That means the bubble shape is not affected by the gravitational force, at least at 1 millisecond, in both pure and partial DNS. And in the result of pure DNS, micro layer profile are almost same between these three cases with different gravities. Next one is a force balance for the case 10G, and left figure shows a pure DNS and right one is a partial DNS. And in case of partial DNS, we can capture the full micro layer evaporation at around 4 microseconds. And at time here, the neck starts shrinking. And at the end of the simulation, the bubble departs from the wall. The blue line is a buoyancy force, orange pressure, and green adhesion force. The total is a red one. And if we see the red line, the F total is almost zero for entire period. And if we see green line here we can see some value here when the neck is shrinking. This represents that we could capture the contact angle hysteresis. This is a force balance for zero gravity force. The buoyancy force is zero for this case. And the red line, the total force is again almost zero. And after full microlayer evaporation, at this time, the bubble shape relaxed to be equilibrium shape. That means approaches to spherical shape in this case. This is a result for anti-gravity force. And in this case, again, the red line, the total force is kept almost zero. And in this case, the buoyancy force continues to decrease because the bubbles continues to grow because the bubble is pushed against the heated wall due to the buoyancy. Here I show the volume evolution for different gravity cases. So we can see the big difference between due to the gravity force and micro layer evaporates. This dashed line represents when the micro layer fully evaporated. And you can see it's a big difference here. So conclusions. Butch's finding F equals 0 is true even under different intensity of gravity. And the bubble departs due to zero bubble bottom area. That means the neck area of the bubble becomes zero. And bubble departs not due to F total is larger than zero. The bubble shape, microlayer shape, and the growth rate at the beginning are not influenced by gravity force. They are more controlled by the microlayer evaporation. So our next target is sensitivity study to quantify the detachment diameter under different conditions. For example, different heat flux, system pressure, surface tension, subcooling, and flow boiling. Thank you very much for watching.